All right, so I think we are ready to start the last talk of our afternoon session. It's a great pleasure to introduce Peter Plechac from University of Delaware. I think also Peter doesn't really need an introduction, but nonetheless, he is of course a very, very well-known expert on uncertainty quantification, on multiscale modeling, on statistical mechanics, and yes, and I'm very much looking forward on learning about estimating linear response and sensitivity analysis of non-equilibrium steady states. Please go ahead.
Thank you very much for this keen introduction. I hope I will live up to the promise. So yeah, I'm sorry, my talk will be a bit out of the scope of the previous talks, although there is a connection to statistical learning, which goes in what I will talk about today, in the estimating essentially the derivatives of expected values. And as Christian mentioned, it's also related to some problems in sensitivity analysis or uncertainty quantification from the local point of view. But I selected this title because I want to actually show some specific applications which are more geared towards computational statistical mechanics. And as for the topic of the workshop, I think it will be mostly on the side of this stochastic numerics part rather than the learning part. So this is a joint work with my former postdoc, Ting Wang, and our collaborator and friend from Paris, Gabriel Stolz. And we have been developing this and applying this sort of methodology of using likelihood ratio methods for estimating of these derivatives of expected values, derivatives with respect to parameters over the last couple of years. So there are also some publications related to it, which I listed right at the beginning. So I will motivate the technique and the problem by a question in statistical mechanics simulations, and that's an estimation of certain transport coefficients, which are done by the method which goes under the name linear response. And then we will see how this is connected to the sensitivity analysis in stochastic dynamics. I will say a few words about the general principles for computing averages in ergodic systems, and then I will talk mostly about this likelihood ratio estimators which we have developed and how they should be implemented in the numerical schemes for integrating or approximating the solutions of stochastic differential equations in the way that the scheme is consistent with the numerical discretization of the underlying SDE. And then if time allows me to show some examples, I'll show examples with Langevin dynamics and some transport coefficients in molecular systems. So I should say that, of course, estimating sensitivity of or estimating perturbations of the dynamics is quite common task in many applications, for example, in finance. The difference in this talk will be that we are interested in estimating sensitivity with respect to the stationary distribution of the dynamics. And that stationary distribution may not be actually known in any explicit way. So in practice, it can be accessed only through the simulation, a long-time simulation of the underlying dynamics. So so you can view it as a sort of infinite finite time horizon problem. So in a kind of mathematical formulation, we will look at a ergodic Markov process which depends on some parameters, epsilon, and it has an invariant distribution, which I will denote mu. And for a given observable or given function on the state space, we will look at the derivative of the mean of this observable or the expected value with respect to this parameter epsilon. So nothing mysterious here. This is just the definition. We perturb the parameter and we want to compute the derivative at that value of the parameter here chosen to be 0. So as I said, this mu in our simulations can be accessed or sampled only as a long time limit of the underlying dynamics. So this derivative or this quantity kappa f sometimes goes under the name of sensitivity index, but in general, what we want to get is really the derivative of this expected value with respect to some parameters. So it also has applications in stochastic optimization, or in the context also some learning problems. We have been trying to develop this method for some problems in reinforcement learning and so on. The main focus is really on estimating these gradients and have estimator which will have a low variance. Ideally, variance which will not depend or which will not grow in time, because as I said, in practice, we have to run the underlying process or underlying dynamics for a long time, and the variance should not be increasing in time. So as I already emphasized, we are in the situation where methods developed for finite time horizon problems in the sensitivity analysis are not directly applicable. So we really want a method which can handle this large time simulations. So as I mentioned, this has many applications. The motivating application for us was estimating these transport coefficients in molecular systems, because that is a known difficult problem where estimators of steady state sensitivity, so transport coefficients, suffer from large variance. And again, if the system is not at equilibrium, so the dynamics is not reversible with respect to this stationary distribution, the Boltzmann distribution, then the only sampling which can be achieved is through this running very long time dynamics, which is defined by this Hamiltonian system with a Langevin thermostat. And we wanted to also kind of compare this linear response computations based on our sensitivity estimators with the standard method in this industry, which is the Green-Kubo formula or Green-Kubo estimators. So, just a couple of examples. The estimates for transport coefficients like mobility or shear viscosity, they have a specific form in this Green-Kubo formulation for particular choice of these observables f, and the Green-Kubo estimator requires to compute estimates with respect to this equilibrium distribution of these correlation functions. Again, the time interval has to be truncated, but depending on the decay of these correlations, it can be pretty large. So again, requires large estimation, large time horizon. So we will see this sort of linear response theory for Langevin dynamics. So that's a Hamiltonian dynamics with a thermostat called Langevin thermostat, which allows to sample from the canonical distribution. And the linear response here is achieved by perturbing the drift in the P component of this dynamics by a suitably chosen force field F. And it's important to notice that this F may not be of gradient form, so this perturbed dynamics doesn't have to be reversible with respect to its invariant measure. So what are the computational challenges? As I said, the dynamics has to run for a long time to sample the stationary distribution. And then we need to find how to approximate the derivative with respect to this parameter epsilon to actually find a formula for this linear response and study the variance of the estimators, both for the derivative and also for the mean of the observable. So, okay, let me just move. So as I said, this estimating parametric sensitivity is a fairly common problem with many applications and different approaches. At the finite time horizon case, we can always use the finite difference approximation, of course, simulated two different values of the parameters. Here, in our context, it's probably not a good method of choice because, as I said, estimating each of these perturbed and unperturbed expected values requires very long simulation. And in the pathwise approach is also not really suitable in this case because it's difficult to apply it in cases where we don't have a reversible dynamics. So we will study the approach, which is based on likelihood ratio, which essentially means to construct a reweighting process, the log likelihood process Z, for our perturbed dynamics and use that for estimating the parametric sensitivity of this observable F. So the question is, of course, whether if we use the time averaging, because we have this ergodic system, so we can construct an estimator which is based on time averaging of the observable reweighted by a suitable process Y, which should be an analog to this log likelihood process for our dynamics. And the advantage of this approach is that we will simulate only the unperturbed process. Okay, and we will have to show that, of course, that this limit really converges to the right quantity, which is this sensitivity index or the transport coefficient. So that's not immediately clear whether we have the result like this, that at the limit this will compute the right quantity. And another question is what will be the variance of an estimator of this form. So let me first say a few words about results which are well known, and that, of course, in this ergodic process or ergodic dynamics, we can estimate the mean, the expected value of the observable in this t goes to infinity limit and approximated by truncation. And these are well-known results and also analyzed in the context of the numerical scheme by a nice paper by Mattingly, Stewart, and Plechac. We know that the bias decreases as 1 over t, where t is the length of the simulation or the truncation, and the variance of that estimator, of this estimator here, just the time averaging on the single realization, the variance also decreases as 1 over t. So that can be then related also to the numerical discretization of the underlying dynamics and the scheme, which say if you use the first order scheme with the weak error of order 1, of order h, we will get a similar relation between the bias and the discrete, the quantities obtained from the discretized dynamics in the kind of consistent way. So the bias will be again of order 1 in h, and the variance and the statistical error will be also of order h, not the variance of order h squared. So these are known results, and it would be nice if something similar happened also for estimating the derivatives with respect to parameters of these observables. Well, unfortunately, that's not the case. So our goal is to essentially derive similar results now for the derivatives of the observables with respect to parameters and find what is the kind of consistent construction of this reweighting process. This reweighting process, of course, in the finite, in the continuous time, is a log likelihood process, but it's not immediately obvious what is a right construction when we deal with the discretized dynamics, discretized stochastic differential equations. So in a general setting, we can view the stochastic process as a solution of this stochastic differential equation with the perturbation in the drift. So that will lead us to the construction of that reweighting process of likelihood process Z as the derivative of this Radon-Nikodym derivative with respect to the parameter epsilon. So of course, if you look at the perturbation of this type here, then we can use Girsanov's formula to compute that reweighting process Z explicitly. And now this calculation suggests that we can indeed have a estimator which is based on time averaging, and maybe we still need this expected value, this ensemble averaging to obtain the correct value. So for that, we can prove two results. First, that we are approximating the correct value, but the convergence of this process as t goes to infinity is not almost surely, but we have a convergence in expectation, and we can also show that it's not, there is no bias. This is an unbiased estimator, but unfortunately the variance of this estimator grows with the time t. So in this form, this estimator of the derivatives would not be useful because, as I said, we need to take t very large. In principle, t has to go to infinity. So that brings us to the kind of modification, which we called a centered estimator. And there are two versions. I will talk only about this first one, which is here in red. So the reason why it's called centered is that we center on the expected value, on the mean of the observable in this first piece, and then it's reweighted by the same process. And that the result, which we first obtained for continuous time Markov chains at the same time, where Glynn and his student Olvera Cravioto had a similar result for discrete time Markov chains, shows that while the variance of uncentered estimators grows linearly in time, the centered version has a bounded variance. So that's an important property which makes this approach useful, because also the variance can be quite large. We can beat it by this independent sampling on this expected value here. So unlike for the ergodic averaging of the observables, we cannot use just a long single trajectory. This requires averaging over the independent trajectories in practice, and that helps to control this constant variance. So just okay, I'll skip this because we return to some examples later. So there is also another much kind of mundane explanation why this centering is good choice. It's actually the optimal, asymptotically optimal control variate for these uncentered likelihood ratio estimators for the sensitivity. So that in some sense is an optimal choice. Okay, so now let me just quickly say a few words about the simple construction of this likelihood ratio, log likelihood ratio process for this case of stochastic differential equation. So as I said, using Girsonov theorem, it's easy to construct the process Z directly as this ethos integral using the perturbing field or perturbation of the drift F. So one of the advantages of this approach, as I said, is that we never simulate the perturbed process. We just work with the unperturbed dynamics. Maybe a bit of about the proof, or the technique, how to show that that estimator which we designed really converges to the sensitivity index of the observables with respect to these parameters, so to the linear response. The technique is based on using the Poisson equation associated with this process, with this stochastic differential equation, and analyzing a bit of the properties of this Poisson equation defined by the generator of the process. Okay, so I'll skip this so we can move to. Okay, there are some technical steps. The important result, as I said, is that the centered version has a bounded variance in bounded in time variance. So that makes this approach practical. So now, where does the numerical analysis or numerical approximation enters? Is of course that when we simulate, we discretize the differential stochastic differential equation, and we would like to see whether we can achieve some sort of consistency. So if the scheme, let's assume that we have one-step numerical scheme, if that scheme has a weak order alpha, that we would like to see that the bias on has using this discrete version of our estimator has the same order as our numerical scheme. So natural choice of the scheme is, of course, that we replace that continuous time version of the estimator here with its discrete form. The question is, what is the right form of this discrete reweighting process? And you may say, okay, we have a formula for z as a Ito integral, so why don't we just discretize that and use the discrete version? So it turns out that this needs a bit of work to achieve this consistency in the bias, because for the first order scheme, so weak order 1, then indeed this reweighting process y can be directly the discrete version of the Ito's integral that defines the process z. But if we use the higher order schemes, then this process y has to be some modification of this continuous time process z. And that comes with, again, the analysis of the discrete Poisson equation associated with the discretization scheme, and requires a bit of care, because we eventually write that estimator, written here, as a product of two martingales, or martingale increments, to be more precise. Okay. So the discrete approximation has this form, and one has to analyze a bit more carefully the expansion of this martingale product term in the discretization parameter h. And of course, that becomes a bit convoluted, so it requires a bit of developing some sort of calculus to properly handle all the terms in this discretization analysis. But at the end, it's possible to collect all the terms in the corresponding Taylor-Ito expansions and analyze which terms needs to be included to achieve the right cancellation in the expansion of the approximation of the sensitivity index in terms of h. And that leads to the modification of that reweighting process for the discrete scheme. So in summary, well, if you look at the simple case where the underlying dynamics is an elliptic generator, and we use the Euler-Maruyama scheme, so weak order 1, we found that the right form of the estimator is, as I said, exactly what you would expect. You just take a discrete version of the process Z, and that defines the reweighting process Y, and the result is what you would expect. The bias is of order 1, and the variance is constant in time, and it also has the order H, as in the case of the discretization error for the statistical. But if you use this, if you use the second order scheme, here is an example of one second order scheme, we will find that this has to be modified to achieve, again, the consistent second order error in the bias of the estimator. And we see that now there are some additional terms which needs to be added to the definition of the reweighting process. So why do we care? Well, you may say this is not such important. So that brings us to this example of Langevin equation. So the sampling in the case of molecular dynamics or molecular systems at thermal equilibrium. So the reason is that for Langevin equation, the standard scheme, the kind of splitting schemes used for in all the molecular dynamics codes are of second order, weak second order. So we would like to have that this estimator is also actually achieving this second order error in the bias of the estimated sensitivity. So again, the same analysis as for that elliptic case now applies for the case of Langevin equation, for which the generator is not elliptic, it's hyperelliptic. So for the first order splitting schemes, we will get again the same kind of result, that the reweighting process is just a discrete version, straightforward discrete version of the log likelihood process. But for the typical second order splitting scheme, which combines the three steps of the Langevin equation, so the standard Verlet scheme for the Hamiltonian part and Ornstein-Uhlenbeck process in the approximation of the thermostat process, we find that the reweighting process actually depends on the form of the perturbing field. So again, becomes a bit more complicated for a field which is dependent on both momentum or momenta and positions. But just to present some formula for the perturbing field which depends only on positions, you see that this discrete part of the log likelihood process is corrected or is modified by another term which comes from this gradient of the perturbing field. And in this case, again, we obtain the consistent bias as a second order in the discretization parameter H, and the variance stays constant in time. So again, that's an important property which makes this really of practical use. Just to show that there is really some calculations. There are really some calculations involved in deriving systematically what this reweighting process should be. I can show you a more general formula, and you see that it really requires some theory-oriented way to organize these asymptotic expansions to be able to derive more general cases. So just a comment that this is really of some use is if we compare it to the Green-Kubo estimator, which, as I said, is an estimation of these correlation functions. This can be also centered, but even with the centering, the variance of these estimators grows again linearly with in time, or with the number of time steps. So in principle, our estimator can be much more efficient. Of course, that depends on a particular observable and the rate of decay of these correlations, because that limits, or this allows us to truncate this infinite time horizon integration here. So in some cases, we get a gain in terms of controlling the statistical error in these estimators. Okay, let me end with some examples which will demonstrate that there is some gain. So this is a simple small system with periodic potential. So which compares the estimation of mobility or diffusion constant in this simple system, and it shows the comparison of well, first it shows that we can recover the correct rate of bias, the convergence rate. So we see that the second order approximations really recovers the second order rate in bias for this martingale product estimator. That's how we call these new types of estimators. While the Green-Kubo estimators, the Green-Kubo estimator of first order again gives a first order rate. The more interesting part is the dependence of the variance. The red and the blue curves show that indeed the variance of Green-Kubo estimators grows in time, while the variance of this second order martingale product estimators stays constant. And it's much smaller than the variance of Green-Kubo estimators. And if you look at the root mean square error, we see that indeed the martingale product estimators can outperform Green-Kubo even in this simple low dimensional problem. So as I mentioned, one reason for all this numerical analysis and trying to have a consistency in these estimators was to recover the same approximation error for estimating the derivative. So I would just use this example here to show that indeed it matters how the reweighting process is constructed. So here we use the second order, again, Langevin dynamics splitting scheme. And you can see that if I use only the green part of the construction of the reweighting process, as I said, this is a straightforward discretization of the formula from Girsanov theorem, then we will get only first order, that this green line here, first order convergence with respect to the discretization parameter. So although we are running the second order dynamics, but the correct construction, which comes from our analysis, adds this red term in this particular case of the observable, and with that we, as proven, we recover the consistency, we recover the second order scheme again. So in this case, you also see that that gain is one order of magnitude in estimating this sensitivity index, which is fairly significant improvement when it comes to estimating the transport coefficients. Okay, so I'll stop here. I'll leave these concluding bullets here. What I would say, the take-home message from this is that when you estimate the derivatives of observables with respect to parameters in your stochastic system, you should use, and you want to use likelihood ratio or log likelihood ratio approach, you should use the centered estimators, because they will give you for large class of problems the bounded variance in time. So that's important for the case of estimating these sensitivity indices with respect to the stationary distributions. Okay, thank you very much for listening to my talk, and I'm ready to answer questions.
Thank you very much. Thank you very much for this great talk. I was struggling with the microphone for a second, but yeah, are there any questions?
Ahoy, Peter. This is Raul. How are you?
Ahoy, ahoy.
Thank you for the nice talk.
Thanks, Raul.
Peter,
yeah.
Could you comment on the possible use as an alternative of the first variation to represent the derivative?
First variation, okay. Yeah, you could do the first variation, but if you do the first variation for this particular linear response, so the perturbation in the drift, you will just end up with the same process as this likelihood process, and you would have to you just get back to the Gersonov formula.
So they're equivalent in this case.
In this case, they are equivalent. Of course, if you wanted to do the variation with respect to I mean, if you want to do the linear response with respect to the temperature, for example, in this type of then you cannot do, well, you can still do it here for Langevin equation, but of course you cannot perturb in sigma, in the noise term. You will not get the Gersonov theorem.
And then you will get something that is useless or not equivalent, or what?
I mean, you can do it for finite time horizon. You can do it for finite time horizon at the discrete level, and then look. So when you discretize, you can still do this kind of variation type of formula at the discrete level, and then modify it later to find what and to get a modification that you can pass to the limit as h goes to 0, and you essentially derive something which is like Maliavin derivative type approach for the variation in sigma. but if the perturbations are only in the drift, which was our kind of main focus, then you don't gain. It's equivalent to this likelihood ratio.
Okay, thank you.
Are there other questions?
It's not really a question, but maybe a clarification, actually a request of an extra explanation. I haven't fully understood why in your estimator you don't need to solve the forced system, but you can actually get away with the unperturbed one. Could you?
Oh, I see. Okay, so yeah, that comes to essentially this calculation here. So, or even here, maybe here. So it's a change of measure or Girsonov type of argument here, that the perturb system has this measure P epsilon, and you can compute the Radon-Nikodym derivative, which corresponds to changing the measure for this process to the one without the epsilon, or epsilon equal to 0. So by that, if you think in terms of change of measure formula in this expected value here, the expected value is under this P epsilon, but here is under the P, so epsilon 0. So you will get this weight, which is this process Z, this reweighting or block likelihood process.
Got it.
And for, of course, for this particular case, using the Girsonov formula, you have an explicit form for this L, and then you differentiate, and then you get Z, and that's how this F comes to the game here. But this expected value is under the P, so you just simulate unperturbed problem.
Got it. Thanks a lot.
All right. If there are no further questions, then let's thank Peter again for this very, very nice talk.
Thank you. And I'm really sorry I couldn't make it this time. Maybe once I will be able. Raul, thank you very much for inviting me.
I think I can say, even though I'm not one of the organizers, it was a pleasure having you. Thanks, and see you all tomorrow.
Bye-bye. Bye, everybody.
Bye-bye.